Good afternoon, ladies and gentlemen. Welcome to my talk. My name is Bernd Zeiß. I work at Gerresheimer in the field of prefillable syringes. Thank you for joining this talk. My talk is about some technical aspects of prefillable syringes. And my first question would be, has anybody of you, is he already in the business of prefilled syringes? Okay, most of all probably. Okay. So I just want to give a short introduction into the Gerresheimer group. Who is Gerresheimer? Tell a little bit about the syringes we have, which are glass syringes and also syringes made of COP, which is a certain plastic material. I tell you a little bit about some technical aspects, especially regarding the syringe itself. So siliconization, tungsten levels, like what is what's important for the syringe. And at Gerresheimer we currently carry out quite a big syringe functionality study, and I will present some results of this study. Okay, so Gerresheimer is a well-known company in the field. We have about 11,000 employees in 47 locations worldwide. Gerresheimer at the moment is restructured a bit, so that we will have 3 divisions from December onwards, which is the primary packaging, which is lab glass department, and also plastics and devices. So what about the syringes? Syringes, you know, are both. They are not only primary packaging, but they are also kind of a delivery system for a drug. So they are both. I come to that later. The prefillable syringes we have are from glass. They are manufactured in the site in Bünde in Germany. In Bünde we have the so-called RTF syringes, ready-to-fill syringes, which are sterilized and ready to fill for the pharmaceutical company. We have about 850 employees at this site. Regarding the plastic syringes, the COP syringes, they are not directly from Gerresheimer, but from a company called Taisei Kako, which is a partner company. And in Europe and also in the US, in the markets out of Japan, we are supporting this COP syringe. Taisei Kako has about 900 employees in Osaka in Japan. The syringes are called ClearJect syringes and made of COP. Yeah. So the difference, there's a big difference between glass syringes and COP syringes. This is a picture from the manufacturing in Bünde. You see, I think I cannot walk away from this microphone, and the laser pointer doesn't work, but I think you see that quite well. So we have the glass barrel forming in Bünde, and we have the processing later on, which we call the RTF processing, which means the syringes are washed, siliconized, a plunger or a tip cap or needle shield are put on, and then they are put in a tub and sent to sterilization. This is different from what is done with the COP syringes. The COP syringes, basically, it's actually a lights-off production in Japan. So in this machine in the front, you put in the resin, the COP resin, and in the end you get out the packed syringe in the nested format. So there's no hands, no people involved in this process. And then they are shipped to sterilization, of course. So currently most of the syringes in the market, actually more than 90% out of Japan, even more than 95% are glass syringes in the prefillable business. And only a minor part is in the COP syringes. COP is the material which you can use also for long-time storage. Other plastics do not work to store drugs for, say, 2 or 3 years, so you need to go for this special plastic. So COP is still a niche product. The question is, will it become a big player in this field, or will it remain a niche product or only be for certain applications? We don't know yet. The market is developing, but there is nothing, no big trend towards COP to be seen currently. So you can compare these both materials. They are very different, glass and COP. You have, first of all, you can divide them chemically and physically with the chemical and physical properties, and also regarding production and processing. They are really different. And sometimes glass has an advantage, and sometimes the COP has an advantage for a certain application or for a certain drug. So, for instance, the barrier properties. Glass is the benchmark. The glass is absolutely inert. There is no gas going through this material, and there are slight disadvantages with plastics and also with COP. So it's not absolutely gas tight and not absolutely tight for water vapor. Looking also in the production or the processing, there are also differences. Glass, of course, is prone to break. It can break in processing, but also at the customer in the end. Plastic and also COP is break resistance. So you can make up this matrix and look what is the right material for your application, if it's glass or even COP. Okay, let's talk a bit about the glass syringes. The glass syringes we call RTF, ready to fill. The components we have or we ship to the customers are tubs. So it's a nested, the syringe is nested in a tub. And inside in this tub we have the glass barrel, which is washed and siliconized. We have different formats from 0.5 to up to 3 ml actually. There is a closure system assembled, a needle shield or tip cap. And you can also have needles inserted. The whole glass syringes, or all glass syringes, are sterilized by ETO gas. We also offer some accessories like backstops, so that you cannot pull out the plunger stopper from the syringe if you have harmful drugs. For instance, we offer plunger stoppers, which come not directly from us, but from the well-known suppliers in the field. And we also offer the plunger rod so that you can get the whole syringe also from Gerresheimer. Okay, let's switch to some, the special applications. Currently, or where do we come from? The glass syringe originally was designed for mainly vaccines and also for heparines, which are not very demanding drugs. But currently and also in the future, more and more biotech drugs will be filled into prefillable syringes. And this causes some really some challenges to the current barrels or the current syringes. For instance, silicone oil particles, tungsten residuals. So with the glass, if you form a glass syringe, there's always a tungsten pin needed to open the bore in the cone. And you will always have some residuals of tungsten in the syringe. And tungsten can cause, in rare cases, can cause aggregations or deactivation of your drug product. So you have carefully look, is your drug product affected by silicone oil droplets or tungsten residuals or glue residuals or what you have. So what we do at Gerresheimer, we try to optimize the syringe according to your requirements. We do a lot of customized versions. So currently we do not have this solution for biotech drugs or this solution for non-demanding drugs, but get in contact with us and discuss with us what is your need, and we will basically design a syringe according to your requirements. Let me tell you, or the next slide will show you some findings we have regarding silicone oil particles, because silicone oil is always needed in syringes. So silicone oil is needed as a lubricant in the syringes. There are three parts of the syringe in contact with silicone oil. It's the barrel itself inside. It's the elastomers, the rubber components. They are, in most of the cases, they are siliconized. And also the cannula is siliconized on the outside to get it into the skin without hurting too much. So actually silicone oil is almost everywhere. But it can be reduced or it can be changed chemically not to get into solution. And how is Gerresheimer addressing this problem? How can this silicone oil load be reduced? What we do, we have a patented process called baked-on RTF siliconization. So there are plenty of possibilities to put a baked-on siliconization on a syringe. But the process we have reduces the siliconization or the load of free silicone oil particles dramatically. So coming from, you see the blue bars here. Coming from the blue bar, which means a standard siliconized syringe in a 1 ml long syringe, that's 0.8 milligrams of silicone oil. You have, say, 100% of silicone oil droplets, and with a so-called baked-on siliconization, which is a baking process of a reduced amount of silicone oil in a baking oven, basically, we can reduce this amount of free silicone oil droplets down to 7%. So you have less silicone oil particles which can interact with your drug. So this is how we address this. But you as a pharmacist or a formulation developer, you have to find out, is my drug, is it affected by silicone or not? So this needs to be checked, otherwise you are fine, very fine with a standard siliconized syringe. We also carried out some more testing with that, not only with WFI shown here, but also with the Tween 80 solution. We did a transport simulation for 3 months, simulating the shaking of the system on a truck. So, and of course, shaking also causes more silicone oil drops. We have a lot of data on that. Yeah, another challenge to the syringe is the functionality, not the interaction as a primary packaging, but more the device side of the syringe. So the syringe needs to work fine. So imagine a doctor. I think I have a syringe in my pocket here. Imagine a doctor who wants to administer a syringe to a patient. Of course, he expects that the syringe has a absolute constant and reliable gliding force, so that he doesn't have to press hard with one syringe and press less hard with the other syringe, but he expects, of course, a constant gliding force. And this aspect, telling ease of use, is something we really address in a big study we're carrying out, which is a syringe functionality study focusing on gliding forces and break-loose forces. And once again, we can optimize the syringe system together with you as our customers. What we cannot do at Bünde, at our side, is fill drug. We can only work with WFI or with empty syringes. But we can optimize the syringe with the possibilities we have. Let's have a look at this ease of administration, I called it. So this is how a gliding curve looks like. Wait a second. So when I empty the syringe, a machine can detect what the gliding force looks like, and it basically looks like this. This can be very, very different from syringe to syringe, depending on what setup you're using. So the gliding curve could also look like this. This can be very, very different. And we carried out testing with about 20,000 syringes on different setups and combinations and have data on that which we can share with you as customers to find the appropriate syringe system for you. That's how the syringe study looked like. We had 1 ml long syringe, 1 ml short syringes, all with the stake and needle in this study. There was siliconized spray siliconization with spray siliconization and with the baked on siliconization. You know it already. They were empty, which is something we can do or we do anyway in the factory for quality checks. And we had filled them with WFI. We had stoppered them with the two important stoppering methods, which are vacuum stoppering and vent tube setting. And we had plunger articles from two manufacturers with all different designs and rubber formulations, coated, non-coated, you can imagine. So we have a very big study carried out. Also, we looked on how does the syringe or the break loose and gliding force behave at the T0, so at directly after filling. And we looked after 3 months, after 6 months, we made accelerated aging tests and so on and so forth. So we have a very broad database by now to find the best and appropriate syringe system. On this slide you see a comparison between the break loose and gliding force of a baked on syringe with a baked on siliconized syringe, sorry, and the spray siliconized one, and you see that the baked on has slightly higher gliding forces compared to the spray silicone, which is clear because there's much less silicone oil involved. But the gliding force is still in the range fully acceptable, especially also for auto-injectors, which need a constant and not too high gliding force to release. You see with the dotted line even that after 1 year there is no increase in the gliding force, but even a drop down. So storage does not have a negative impact on this syringe system. What I have to say is you cannot generalize this picture. It can be very different from plunger stopper to plunger stopper. So using another plunger stopper with another rubber formulation, for instance also from another manufacturer, can, with this combination, show another picture. So you have to look very much into detail which is the one that fits for my purpose. We was astonished ourselves how unclear this all was. So it was no general trend, but very, very depending on the combination. Anyway, I tried to sum up some general trends. And what we could generally say is that the gliding forces are lower in the spray siliconization than in baked on siliconization because of less silicone oil involved in baked on. The break loose force, so the force causing the first peak, there was no general trend, no difference between the two formats of spray or baked on siliconization. You saw already that the particle amount was much higher in spray siliconization than in baked on siliconization. We also what we did not see was very much difference between the vent tube and the vacuum setting. It can be different from case to case. So if it's important for you, or if you are fond of one of the stoppering methods, you should look into these special combinations. What we definitely saw is that the influence of the plunger stopper was very high. So all three arrows are very long. The storage did not have a very big impact after 3 months. So what I want to say is that after 3 months of storage, we could already see that the syringe has a stable condition. That's not getting worse after 3 months, in most cases. Okay, that's maybe the most important chart to take home. So choosing the right rubber formulation can make a difference. So don't say, I want this syringe and that syringe, but also check the right combination of the syringe with the rubber. Okay, let's get to the summary already. So what to take home message maybe, there is a wide range of different syringe formats, both in glass and also in COP. There are really many aspects, technical aspects involved in the syringe functionality. So you have to know if you go for an auto-injector, if you have a product that is in a way expensive and demanding or not. And based on this information, we can help you to find the right syringe combination. So the break loose and gliding forces, okay, they are very important, give a picture of the stability and the quality of our process, but they are also very important, of course, for the nurses and the doctors who make use of the syringes in the market. And our gliding force study aims at collecting data as far as we can to find the best syringe combination. And we also want to build our expertise and generate long-term data on these combinations. So I think I've mentioned it several times by now. So if you want to tailor a syringe, you have to check every individual combination and just address this at us, and we try to help to find an appropriate syringe combination for you. Thank you very much. You're welcome also to come to our booth. I don't know the number exactly now, but it's this way and it's not the small one. So just come there if you have questions. I'll be there also today and tomorrow. And if you have questions now, please feel free. Okay? Okay, the question was what would happen without silicone oil? And without silicone oil, in the case of these glass syringes we have, the stopper would just clog. You would not be able to put it into the syringe. It wouldn't work. The glass would break or it doesn't work. So you need a kind of lubrication. Yes, also in plastic syringes, in almost all plastic syringes in the field, silicone oil is used. There are some exceptions, but the most cases in COP syringes also silicone oil is involved. Okay, thank you very much.